you for the great opportunity to speak here. So today I will talk about linear varieties, curves, and coordinates.
Yes.
And some classical notions that should be well known, but I will recall them anyways. And then also some things that are less well known, and in particular the main theorem. But the main theorem of the talk will come a little bit later. So let me just first explain more or less the general framework where we are in. So these are the things that we're going to talk about. Hopefully I will remember in logical order. So first, let me say something about the linear varieties. So Abelian varieties, they appear very naturally in algebraic geometry. Why? Because they are algebraic, they are groups, they are smooth and projective. And if you put all those structures together in a compatible way, you get linear varieties. So to repeat, they are group varieties which are smooth and projective. But in this talk, we will focus more on the analytic approach. And so we start with complex tori. So what is this? So this is a complex torus is simply the quotient, I will call it A already, of some complex vector space by a discrete subgroup. So here V is a complex vector space, and lambda is a discrete subgroup such that if I tensor lambda with R, I get the entire vector space. So as an example, you can think of C modulo Z I. So in this example, you see that if you tensor this with R, you get C. It's now inside C. Okay, so that's a very simple definition. And in this case, we can also see, so here, if you would draw this topologically, this would be Zi. And then taking the quotient of C by this lattice means that we identify, we glue everything, and so you get this as a fundamental domain. This would be your torus, and that's where the name complex torus comes from. But we look at higher dimensional analogs of this picture. Now there is naturally a so-called Hodge structure appearing here. We have a variety here. We can look at this at the decomposition of lambda tensor C. Okay, so what is this? Well, now actually we see that this is lambda tensor R, that tensor R C. But this we know by the definition is going to be V. So we have a complex vector space which we tensor over R with C, and then it's exercise linear algebra. This is V plus V bar. So there's a natural decomposition here, in the sense that we have V itself, and we have V, which is also a V bar, which is actually V, but where C acts by letting lambda as lambda bar. So here C acts by lambda x, lambda x, and here you get lambda x. So this is a decomposition that you, in fact, get for free in here, and this is, yeah, this is in fact a Hodge structure. Of weight -1. What does it mean? So we have a structure of discrete finitely generated. So we have a finitely generated free unit group, and we have the decomposition of its complexification into two pieces. Where one is the complex conjugate of the other. That's exactly what happens here. So it's -1 for this -0 inside. And so what do I mean here? So lambda. It is discrete to be, it's a linear group. If I tensor with C, do we have complex conjugation here simply by applying complex conjugation on the complex side. And so this is the complex conjugate of this space. This is an example of a Hodge structure. So a Hodge structure is a finitely generated abelian group, and a decomposition like this, in general, you can have more pieces, but in this case, we only have two pieces. Okay, any questions so far? Yeah, so why is this useful in this case? Well, in this case, we see that this process can be reversed. So we have complex tori. And then there's this pointer if you want, but we just look at everything up to isomorphism to these Hodge structures. So it's -1. So again, by this I just mean free Z module and then the decomposition that satisfies this hypothesis.
And we would say that the structure is on what? On gamma or on lambda? Or on or
I'm sorry, what's the question?
is it an odd structure on something, or it's just we just say Hodge structure?
We say it's a Hodge structure. So a Hodge structure consists of lambda and a decomposition of lambda tensor C.
Okay.
Yeah.
Thank you.
But you're right. You could fix lambda, and then you could say, or you could talk about a Hodge structure on lambda. You could also say that.
Okay. Yeah. And that would be just a decomposition.
Exactly. That would be decomposition. Yeah, exactly. Yeah, and the weight means, so in general, if you talk about arbitrary Hodge structures, you get pieces of this form, but you replace -1 and 0 by P and Q. And you get a lot of pieces, but then you require that P plus Q is always constant. In this case, P plus Q is -1. And in general, you ask that H P Q bar is H. That's the symmetry going on. Yeah, so in this case, we have a complex, whenever we have a complex torus, we can send it to the Hodge structure lambda, yeah, with the procedure that I did before. But this process can be reversed, so I can send lambda to H -1, 0. And this turns out to be exactly an equivalence in the sense that V is canonically H -1, 0. If you start with a complex torus. So in other words, this gives us a bijection of these two isomorphs. Any questions so far? Okay, but these are analytic objects and they're not all algebraic, and we only want to consider those which are algebraic. So what do we say? We then say, okay, suppose that our complex torus A is projective. What does it mean? It means that there exists an embedding of A into some arbitrary dimensional projective space. Okay, so this is projective space. So projective complex tori are exactly these forms, and then suppose that we have this, then we get a line bundle. L defined as the pullback of O of 1. But then I need to say what O of 1 is. So this is a moduli space of lines. So there's a universal family of lines on it. This gives a line bundle, and we take its dual. That's going to be O of 1. So here we have O of -1. This is the line bundle whose fiber above the point is exactly the line that that point corresponds to. And then O of 1 is the dual. O -1 dual. So then this gives us a line bundle on our projective complex torus, and then we can look at this first term class, which gives us an element in the second cohomology group of A. Now, the fact that we have a complex torus, since A is V mod lambda, we can in fact write up to diffeomorphism. We can identify V with R2G and lambda with Z2G. So we get R2G. So what do we get? So we in fact get simply S1 R2G topologically, in the topological sense, right? But then we can completely determine the cohomology groups. Whenever you have a space like this, the cohomology groups, they're all generated by the first cohomology group. So what is this? This is going to be the second wedge power with H1 of the first cohomology group. So H1 we can identify with the dual of H lower 1. So we get the second wedge power of H lower 1 dual. And this dual we can take out. So then we get second wedge power H1 Z and then dual. So these are all canonical isomorphs. Okay. Why am I saying this? Well, now to our line bundle, we can associate an element here, which is now some alternating form on lambda. And why on lambda? Well, here one observes that H1 of A canonically isomorphic to lambda. It's it's the fundamental group of the BNU, right? Maybe to say something about this, okay, maybe saying many things at the same time, but we have A, which is V modulo lambda. What's the universal cover? V. And what's the fundamental group? It's lambda. And H1 is the Abelianization of the fundamental group, but it's already Abelian. So this allows, let me see first.
Nicolas.
It's next to the buckets. Down there, to your right. No, next to the buckets.
Oh, this one.
I think so.
Yeah, okay. Okay. Yeah, so now what this showed is that, okay, so maybe now I write down some facts without proving them, is that the fact that this line bundle is ample, by definition it means that it is induced by an embedding into projective space that corresponds exactly to the fact that this alternating form E that we get on lambda, so it's an alternating form, satisfies is such that if we take the extension I times I look at the C-linear extent, yes?
Is it very ample? It directly comes from.
Yeah, yes, you're right. Yeah. You're completely right. So it's very ample since it directly comes from O1. So we relax that condition,
Okay.
and we say that the power is ample.
Okay. So this equivalence is really for ample, not for very ample.
Yes.
Okay.
Thank you. So lambda is ample, which, okay, by definition means that lambda n is I star O E and 1 some n. Okay. It's not very important. You can think of lambda as being the pullback of O1 along some embedding. That corresponds exactly to the fact that if you look at this alternating form and you look at its C-linear extension, this is a positive definite on E, which is yeah, exactly this first space in this Hodge decomposition. Okay, and this allows us to define a polarized linear variety. It's a pair. It's a pair consisting of a complex torus and an alternating form on the underlying lattice, which is positive definite on the vector space. Right? Yeah. Yeah. Alternatively, I could say that a polarized abelian variety consists of a complex torus and the cohomology class of an ample line bundle. And by what I just showed, these two things are. But now we would like to have some kind of nice structure on the space of all the polarized linear varieties. So maybe we also say that this polarization, so E is called the polarization, we say that E is principal if it is unimodular. Meaning that E defines isomorphism between lambda and lambda. If you want to see this in terms of the line bundle side, you can translate this all from linear algebra to geometry. That's why what makes this theory of linear variety so nice. This turns out to be equivalent to dimension of the space of local sections is exactly 1. But now we have enough information to make a space of all the linear varieties, which is a particularly nice structure. So what are we going to do? So we're going to define HG as the space of B in C 2G, such that so we're going to look at G-dimensional subspaces of C to the power 2G, so that B plus its complex derivative is exactly equal to C to the power 2G. And in here, so we say that this is orthogonal and that this is and here so Q is really the alternating form that 2G defined by the matrix general identity. So I now, instead of looking at lambda, lambda is going to be the underlying lattice of the linear variety. I just say, okay, I forget about lambda for the moment. I really take the free Z module of rank 2G. Then I define the polarization on this, which is supposed to be unimodular alternating form. Which is, so I pick this one, and then because they're up to isomorphism, there is only one unimodular alternating form on a free Z module. So this is the standard one, so this is going to be Q, and then I look at all subspaces of dimension G in here that have this Hodge decomposition property, which is orthogonal for IQ x y bar, and so that IQ x y bar is positive definite on V. And then, so by definition, this is the subspace of the Grassmannian of G-dimensional subspaces of the complex vector space of the Any questions here? So now, what do we have? So suppose that we define AG as so principally polarized Abelian varieties of dimension G modulo isomorphism. And then everything that we've done so far allows us to define a map to AG modulo so how does it work? So we start with A, and then we pick an isomorphism phi between lambda E and Z2G Q, which we can do as all these modular lattices are isomorphic. Then we look at the induced isomorphism between the complexification of lambda and C2G. This is phi C. And then we send A to phi C, which is the subspace. All right, and this map is a bijection. So this is going to be moduli space linear right. Principally polarized of dimension G. Yeah. Any questions? Yeah. And the reason that this is well defined is because SP2G, you see, this is really the automorphism group of Z2G. So if we had chosen another phi, then the difference of, let's say, phi prime, then the difference of phi and phi prime would be an element in here, and so the resulting subspace just differs by the first one up to an automorphism of this alternating matrix. Okay. Now we want to relate this to curves. So by a curve, I actually mean a Riemann surface. Which is compact, and let's say G is G. So topologically, I get this picture. So this is going to be curved, and either turns out to be yes.
Yeah, did you really mean a bit about variety on the left or just the right?
I'm sorry?
Is it a bit variety or just the right?
No, here I really mean a million varieties, yes.
Okay. So the construction already.
It's the matchup of E and Q.
Yeah, so here I ask for compatibility between E and Q. So they are all polarized by this construction.
Okay, but
so this is this space has dimension G plus 1 over 3, whereas the space of okay, so maybe it's here. So the point is that suppose that you would look at subspaces that satisfy this condition, then you get a G squared dimensional space that parameterizes all complex tori. But now I ask for the additional condition that this decomposition is orthogonal for this form, and that means polarizability. So that distinguishes those complex tori from which are just arbitrary complex tori from those which are projective. Yeah, so if we start with the curve, we can associate to it this Jacobian. So how do I define it? Well, we can look at the homology of the curve, and embed it into the dual of the space of homomorphic forms by sending one cycle to the functional sense omega to the integration omega. And as you may already guess, I have Abelian finally generated three Abelian root on the left and a complex vector space on the right. So I can now construct complex stories.
I have a question.
Yeah.
In your HT, the same as Segel's upper half plan.
So yeah, this is kind of the generalization of the upper half plane. But if you take g equals 1, you get exactly the upper half plane.
Okay.
You don't get it by definition, but you can show that the two are canonically homeomorphic if you want.
Okay.
Yeah. Yeah. So which one? Yeah. So this is. So you can think of the reason why those two spaces are isomorphic. Yeah, so now I start with the curve, and I define the Jacobian of the curve as the quotient of this vector space by the homology of the curve. And this is a complex torus of dimension G. And then the question is, of course, is it going to be right? But now I need to give it a polarization, and in the way I define polarizations, I need to define an element an alternating form on the lattice, which is the homogeneous curve, which I can do by taking simply coproduct. Yeah, and that's this construction. In fact, gives me a map. I get the Coleman map. Engine. So this is moduli. So these are the genus curves. Isomorphism, and this map sends the curve C to its Jacob, which is a principally polarized to be right. It's a polarization. This is the polarization in this principle because this pairing is perfect. Any questions here? No. Okay. Then this is made. Now I finally come to the question, which is kind of the leading question in this talk. So, what is the image of the element? And this is a problem which is very old, and it's known as the Schottky problem, and it's very hard. So how can we describe the image? So in other words, which Abelian varieties are Jacobian? And maybe more precisely, how close is an arbitrary variety and Jacobian. So the reason is that these questions are natural is that so Abelian varieties they appear in many places in algebraic geometry because of they're so rich because of the group structure and the algebraic structure that interact together. So it's very and curves are the theory of curves is very well understood. So it would be very nice to relate Abelian varieties to curves because we give a lot of tools to understand them better. So, of course, the first question that you could ask if you look at this morphism, the Torelli map, is what is this map? Is it the most basic properties would be injectivity and surjectivity. So yeah. So theorem is injective. So what does it say? It says that if I take two curves, C and C prime, whose associated principally polarized Abelian varieties, JC and JC prime, are isomorphic as polarized Abelian varieties, then the two curves are isomorphic. But then one you should ask about surjectivity. But then there's the following remark: if the map is surjective, then at least the dimension, so then they would be isomorphic, and then the dimensions of the two spaces would have to be the same. So a natural abstraction for surjectivity would be that the dimension of MG is smaller than the dimension of AG. So the dimension of AG, so this is turns out to be G plus 1 over 2. I can say a few words later why this is, but for MG it's easier to see what the dimension should be. So it turns out that up to taking a suitable finite topological cover, which I'm not going to do, these spaces are smooth. So we act as if they are smooth. In fact, they are not smooth manifolds, but stacks. But let's not worry about that. So since this is smooth, or we act as if it's smooth, to get the dimension, we can look at the dimension of the tangent space. So we look at the point C, which is a curve in MG, and we look at the dimension of the tangent space of MG at this point. So by deformation theory arguments, this is exactly the dimension of H1C. So it's the first cohomology proof of the tangent bundle. Yeah, but then this should be now straightforward. So this is the dual of 2 times. So this is the global sections of 2 times. So of 2 times the canonical bundle. So that's the dimension here. And now we can apply Riemann-Roch. So this is going to be degree this is two times the canonical bundle. So we get plus 1 minus G. And so this is 2 times 2G minus 2 plus 1 minus G, which is exactly going to be 3G minus 3. So this here is Riemann. Right? But then we see that if we take G to be at least 4, if G is at least 4, then 3G minus 3 is strictly smaller than G over 2. Hence the map cannot be surjective in this range. Okay? Yeah, and so really this question really starts to make sense. Now to compare one abelian variety to the other, of course one can say are they isomorphic or not, but there's a somewhat finer variant, which is so-called isogeny. So if A and B are abelian varieties, isogeny is a homomorphism. Left A, which is surjective with finite kernel. Yeah, and then then what one can show, yes?
This is maybe a naive question, but when you take G equals 2 and G equals 3,
Yes.
the dimensions, they match up.
Yes.
Does something interesting happen, or is it still not surjective?
So it's a very good question. So now we know that it's injective and the dimensions match up.
Mm-hmm.
Which shows that if we take the image and we take the closure of the image, it should be everything.
Okay.
So the map is dominant. But then the question is nonetheless, what is the difference between the image and the closure of the image?
Yeah.
But that turns out to be, so okay, you can look in AG, you can look at the locus of Jacobians. That's by definition the image. But you can also look at the locus of abelian varieties, which are a product of Jacobians.
Mm-hmm.
So the point is that if you take two abelian varieties, A1, A2, you can take A1 times A2. This is again a abelian variety.
Yeah.
Particularly, you can take products of Jacobians, and the closure of the image is exactly the locus of products of Jacobians. So to be quiet, I can already make the remark right now. So if you look at the image of the Torelli map, this is exactly the locus of A, which are isomorphic to the product of Jacobians. Of course. All right.
Yeah.
And so what your remark says is that for G equals 2 and G equals 3, every principally polarized abelian variety of dimension G is isomorphic to a product of Jacobians.
Thank you.
Yeah, so, but we would like to, so this already shows that there are abelian varieties not isomorphic to a Jacobian nor to a product of Jacobians. But we would actually like to understand which abelian varieties are isogenous to Jacobian, because that's already very close. That means that the abelian variety could be connected, linked to a Jacobian via a surjective homomorphism with finite kernel. So that's going to be the next question. But now the lemma is that, so let LG and AB the locus of abelian varieties isogenous to Jacobian. Then LG You can write it as a countable union. Subvarieties. So I start with the Torelli locus in here, which is the image of the Torelli map. And now I'm saying, apart from this subvariety, there are just many others, but only countably many. And then any abelian variety which is isogenous to the Jacobian should be in this countable union. Yeah, and the idea. I will prove it.
This union is dense, also, right? Or not?
Yes. Yeah, but that's harder to show. In fact, if you take a single abelian variety and you look at all points isogenous to this abelian variety, it's already dense. Yeah. But that's a little bit deeper than, but it's true. And yeah, so the idea here is that what's the difference of between an isomorphism and isogeny? Well, that's something finite because the kernel of a map. So you suppose that you have an isogeny between an abelian variety. Jacobian, the kernel is finite. In particular, it's a discrete structure that cannot vary family. Yeah, and that's more or less what proves this lemma. So, if you want. If there exists an isogeny between the Jacobian and A, then the kernel is given by some finite group K. But then I can since it's a finite, it's a discrete structure, I can put this finite group into every Jacobian. I can do this uniformly. It gives me a map MG to AG that now sends a curve C to the Jacobian of C minus modulo K, together with the polarization. And you have to check many things, but this gives a new map. And the images of all these maps, that's exactly the locus that we look at. It's countable because these are finite groups that are on so the question is, why would you be interested in this countability problem? But then there's something. Then in the algebraic geometry, it's very often used in the corollary. This LG is not equal to AG. And the proof is, so we know that it's a countable union. And so we apply their credibility. Which may not ring a bell.
But can you not just say for dimensional reasons? Sort of this is a countable union of something?
Yeah, but then you still need to say something. You need still, I mean, a priori, what? I mean, yes. And there's something that you need to say in complex and geometry would be Garrett's category theorem, which says that if you take a countable union of nowhere dense subsets, the union is also nowhere dense.
In a complete space.
I'm sorry?
In a complete space.
Yeah, exactly. Yeah, no, yeah, exactly. So you have a countable union of nowhere dense subsets. Yeah. In a complete space, exactly. Yeah, so this is not going to be cover all of AG just because all these have dimension 3G and 3, and this has dimension 2, 2, and this is inequality. How much time I have until?
Like we started 25.
Okay, 10 more minutes, yeah. Yeah, so this also shows that there are principally polarized, let me just say, there are Abelian varieties not isogenous to any even product of Jacobian. Any other questions? Yeah, maybe as a side remark, it's kind of funny is that Barrett's category theorem actually says that the complement of this counter union is dense. In particular, it cannot be empty. And your remark says the counter says that the countable union itself is also dense. So this gives sets that are dense and whose complements are also dense. It's a strange phenomenon. Yeah, so now we come to the main result. So to phrase it, one can also look at the following picture. So we have a map. From AG to AGK. That sends an Abelian variety to its kth power. So for each k we have such a map. And what's the image? The image are exactly the Abelian varieties that are isomorphic to a kth power lower dimensional. All right. And now in here we can look at again at the Torelli locus. So I defined T. I didn't define it before, but let me define it as. Yeah, closed Torelli locus, so the closure of the image. Okay. And now one could also ask something similar. Now in here, question: are there Abelian varieties? Are there Abelian varieties A of dimension G such that there exists no power k such that A to the power k is isogenous? In other words, can we, for each, so can we find an Abelian variety in here so that no matter which k I choose, I could also go to some other k prime. If I take the k power, the k prime power, and then I look at all Abelian varieties isogenous to the thing I get, can I possibly avoid the Torelli locus? And yeah, if you think a little bit, you could ask, okay, but we can do a moduli count as we tried to do before. But this turns out not to work anymore. The problem is that there are infinitely many k that you should handle. So, dimension count does not work. solve this. Yeah, each G is 4 exists at least before the Jacobian variety and G, such that there exists no there is isogenous to product code. So in other words, answer. Yeah, so this shows that even in this sense we cannot approximate. We can also not approximate the powers of the medium variety by Jacobian. Okay, and then maybe I say, so 5 more minutes or 4 more minutes that are left, I say something about proof. Yeah, and I'll just say something quickly about the techniques. I won't go into the details, but the idea is to apply a degeneration argument. And the word degeneration stands for, suppose that you have some very nice structure, like being smooth, projected, etc. Then you degenerate the structure so that it becomes less nice, singular, for instance. Sometimes if you have a property that holds for a smooth variety, by degenerating it, you get something special for the singular variety, and there you can get a contradiction. So the idea is that assume for contradiction that I'm being a little bit vague here, but I mean that for each either and each k, something like this happens. Or for each a, there exists a case such that this happens. The point is that since it happens for each a individually, you can show that in fact the fact that this happens for each a, you can make it uniform. You can put it in a family. So then the next step would be to show that for the universal family of Abelian varieties, I can look at the k power of this family. So this is a family, so at each point, each fiber is exactly the k power of the Abelian variety that corresponds to, let me see, point downstairs. And then, the question is whether this is isogenous to the product family of Jacobians. If this is true, what you could then do is generate do something of the form of 0, which is an extension of the Abelian variety C star. This is our Abelian variety. And now the isogeny that you have will also degenerate. So now you would get, and here, confused. Come to this. So I'm almost saying nothing here. I'm just saying that since we know that for each Abelian variety, so we assume that it holds for each Abelian variety, we can actually get a similar statement to so-called singular Abelian varieties, actually semi-Abelian varieties. So these are Abelian varieties which are not compact. And if it holds also for those Abelian varieties, we can show, okay, but that's not going to be true. So what we in fact do is we break up the problem in 2 steps. We say, okay, if it holds for Abelian varieties, it also holds for non-compact Abelian varieties, semi-Abelian varieties. These are sort of group varieties that contain a non-compact part, whose quotient is a Abelian variety. If it also holds for these non-compact Abelian varieties, and the next step is to show it doesn't hold for non-compact Abelian varieties. Those are 2 steps. And then maybe to finish the talk, I've been working over C throughout the entire talk, but one can ask similar questions over other fields. Questions: does there exist an Abelian variety over Q bar such that there exists no K such that the K bar is isogenous? We'll probably go. And why is this a question and not a theorem? Because of the argument that I showed before. Q bar is a countable field, so the spare category theorem argument doesn't apply. It's a theorem due to Zimmermann. Yes. Okay, I'll stop here.